Double replacement reactions are pretty straightforward if you understand the idea of cations and anions. Just to remind you, cations are the positive ions in the beginning of a formula, and anions are the negative ions at the end of a formula. And basically all that's going on here is that they just exchange places. Now I've written on here that cations exchange places with each other. And I also wrote down here that anions exchange places, but really if you just do one, the others kind of change in place. So if you look at the general formula over here, let's take a look here. So the cation is A and the cation is B here. And what's happening here is that they're really just exchanging places, right? So instead of AX, you get BX, and instead of BY, you get AY. It's pretty simple, straightforward. Of course, you'll have to rebalance those formulas and then balance the reaction, but that's basically all it is. So let's take a look at some examples here and see if we can do this. So how about this one here? This is copper chloride here, and it's going to be mixed up with sodium iodide, and we want to know what we're going to get. So first of all, let's go ahead and decide what the anions and the cations are. So let's take a look. So the cations are going to be copper and sodium. Remember, we always look for the capital letters there. So I've written it down with black arrows here. And the anions are going to be chlorine and iodine. So let's go ahead and just see what we get here. If we exchange those two, it's pretty simple. So we're going to exchange copper with sodium. So instead of getting copper chloride, you get copper iodide. And instead of sodium iodide, you get sodium chloride. And I went ahead and balanced it here. Remember, the charge is a little different here. So on copper, you have a +2, and iodine was a -1. So that's why I went ahead and put a copper 2 there, iodine, and sodium chloride. So it's pretty much as complicated as it gets here. Let's take a look at another one here. Here I've, instead of putting in a single atom anion, I put in a polyatomic. So this guy, NO3, remember, is nitrate, but it's basically the same idea. So let's just go ahead and keep it simple. Let's not even worry about the anions. Let's just do the cations. So we're going to exchange sodium, which is the cation here, with magnesium here. And so what would we get? If we put the sodium here and the magnesium here, we should get sodium chloride now instead of sodium nitrate, and magnesium nitrate instead of magnesium chloride. Is it balanced here? Let's see. 1 sodium, 1 sodium, 1 magnesium, 1 magnesium, 2 chlorine, 1. Oh, it's not balanced on the chlorine. So we're going to go ahead and balance that off here. And let's just make sure our formulas are right here too. Remember, since, let's see if I can draw this in here. Since magnesium is a +2 charge and nitrate is a -1, we had to go ahead and put 2 of them in here. So I balance it off there. And that's pretty much it. That's a double replacement reaction. Now, remember when we talked about the single replacement reactions and we said, well, just because you can draw it down there doesn't mean that it necessarily takes place. And the way we figured that out was we looked at an activity series table, and it said, in order for the reaction to take place, a more active element will replace a less active element. So you look at who's higher up on the table there, and that tells us if it takes place. Same thing kind of happens with double replacement. Just because you can write it down here doesn't mean they all take place. How can we predict? Well, if you look at the products there, what you have to do is put in their state of matter. And what we're looking for is if something is soluble or insoluble. Insoluble means it pops up kind of as a precipitate. So if a soluble product dissolves in water, we call it aqueous. That's going to be our word here, and we indicate it as AQ. If something's insoluble and turns into a solid or a precipitate, we either indicate it PPT, or most of the time they just put down an S down here, which says that it's solid. So what we're really looking for is a change in the state of matter. That'll tell us if the reaction really took place. Here's a big table here. You don't have to memorize it. It's in the book. Maybe we'll paste one in here. Basically, it says that if you mix these ions with these anions over here, are the products going to be aqueous or will they be solid? And that's going to pretty much tell us whether or not it was a reaction. So we're looking for reactions to have solid products. Let's go ahead and take a look at one here. So how about this one? Calcium sulfate plus 2 molecules of sodium chloride goes to make calcium chloride plus sodium sulfate. Nice, looks good. Is it balanced? Yeah, it's all balanced, that's fine. But the question is, does it take place? So what we're going to do is use that table, and we're going to put in the states of matter there. So calcium chloride, let's take a look here again. Calcium chloride would be right there. Oh, that's aqueous there. And who was our other guy there? It was sodium sulfate. Sodium is down here, and sulfate is there. Ooh, they're both aqueous. They both dissolve in water. So let's go ahead and indicate that here. So they're both aqueous, and that means the reaction really doesn't take place. Even though I was able to write it, it doesn't take place. Let's take a look at one more, and then we'll finish up. Zinc chloride plus sodium sulfide goes to make zinc sulfide plus sodium chloride. Let's take a look. So let's go back up to our table. Zinc sulfide. Let's see, is that going to be on here? Yeah, there it is. Zinc and sulfide is right. Ooh, that's a solid. That's a solid. And sodium chloride is aqueous. Ooh, so let's go ahead and put that in there. So one of them actually is a solid, right? That's a solid. That's really important. So because this is aqueous, and this is aqueous, but this guy popped up as a precipitation, as a solid, that means that the reaction probably did take place. Okay,